Hey chemistry students, this is the last section in our chapter 15. We're going to predict how a system at equilibrium will respond if the reaction conditions are changed. I had to put these couple of funny memes. Let's say we increase the concentration of the products. That means we need to slide to the left. If we increase the concentration of the reactants, we need to slide to the right towards the products. When stress is added to a reaction, the side that has the higher concentration, we need to, let's say it was the products on the right, we need to slide to the left towards the lower concentration or towards the reactants to get back to equilibrium. The equilibrium between reactants and products may be disturbed in three ways. We can change the temperature, we can change the concentration of a reactant or product, and we can change the volume for systems that involve gases. A change in any of these factors will cause a system at equilibrium to shift back toward a state of equilibrium, which will cause the system to change in such a manner as to reduce or counteract the effect of the change. This is called Le Chatelier's principle. It's a shorthand way of describing how the quantities of reactants and products are adjusted so that equilibrium is restored. That is, so that the reaction quotient is once again equal to the equilibrium constant. We want Q to be equal to K. And when something is disrupted, Q might become less than K or greater than K, but we need to get it back to being equal to K. Here's a couple more funny memes. If we increase the reactant concentration, that means we need to shift to the right, just like this guy's hand, towards the products. So if I increase homework concentration, we're going to need to burn some homework. If that stress is applied to a system at equilibrium, the system will react in the direction that counteracts that stress. In other words, the system is a rebel. Let's look at an example here. Assume equilibrium has been established in a 1-liter flask where butane's concentration is equal to 0.005 and isobutane is equal to 0.0125, and we're given our equilibrium constant. Remember, we would have K is equal to the concentration of our product, so isobutane concentration over reactants, the butane concentration. Then we add some more butane, so that's going to disrupt it. What are the concentrations of butane and isobutane when equilibrium is reestablished? Well, let's make our ice table. We were told that butane's initial concentration was 0.005 molar, and isobutane's was 0.0125 molar. But then it says I added 0.0150 to the butane. Because of Le Chatelier's, if I increase the concentration of a reactant, that means that I need to shift to the right and I need to increase the concentration of my product. Think about it. If I have a fraction 2 over 2 to give me a K value of 1, and I increase my reactants. So remember, this is products over reactants. So let's say I increase my reactant from 2 to 3. In order to keep a value of 1 here, I also need to increase my product to 3, right? 3 over 3 is equal to 1, just like 2 over 2 is equal to 1. So if I increase my reactant, I also need to increase my product. So my reaction is going to shift to the right. So I need to lose here and I need to gain here. Let's look at equilibrium. I'm going to have, when I add these two together, that gives me 0.02 minus x, and then I have 0.0125 plus x. Let's set that equal to our Kc. All right, I set it up. We said Kc was equal to 2.5. So I've got my 2.5. My equilibrium isobutane was 0.0125 plus x. My butane, 0.02 minus x. Let's cross multiply. That leaves me here 2.5 times 0.02 minus x. So now I need to distribute and do 2.5 times 0.02 and then 2.5 times negative x. Then I need to get my x's on one side and get my actual numbers on one side. So I'm going to add 2.5x to both sides. Then I need to subtract 0.0125 from both sides. That leaves me with 0.0375 is equal to 3.5x, and divide both sides by 3.5. That gives me x equals 0.01071 molar. Now we need to take this and put it back into our equilibrium values from our ice table. Let's do that. That makes my equilibrium values for butane 0.0093 molar. And my equilibrium value for isobutane is 0.0234 molar. Now let's double check to see if this made sense. I had butane had a concentration of 0.005 and my isobutane was 0.0125. But then I added more butane. I added 0.0150, so my concentration for my reactant increased. That means I need to counteract that, and I need to shift right, and I need to increase the concentration of my isobutane. Let's see if that happened. My isobutane was 0.0125, and it increased to 0.0232. Let's just double check to make sure that our equilibrium constant is still the same. If I did my products divided by reactants, so in your calculator, can you do 0.0232 divided by 0.0093? We should get 2.5. Double check it. Let's try another example. Equilibrium exists between butane and isobutane when the concentration of butane is 0.02 molar and isobutane is 0.05 molar. An additional 0.02 moles per liter of isobutane is added to the mixture. What are the concentrations of butane and isobutane after equilibrium has been attained? See if you can set up this ice table and solve it. Now in this case, because we had isobutane added, so the concentration has risen for isobutane, that means the counteract is that we need to shift left and increase butane. So that means we need to minus x and add x. Therefore, at equilibrium, that gives me 0.02 plus x here, and 0.05 plus 0.02 would be 0.07 minus x. Now let's plug that into our K expression. And for the K, the value of 2.5 I got from the slide before, but if we hadn't known that, we were told that equilibrium was when isobutane was 0.05 and butane was 0.02. So if you did 0.05 divided by 0.02, you'd get 2.5. I plugged everything in. If you want to look at my process as far as distributing and then adding x to both sides and then subtracting the 0.05 from both sides and then dividing both sides by 3.5, I got x was equal to 0.00571. Now I need to plug that into these equilibrium spots. So 0.02 plus 0.00571 and then 0.07 minus 0.00571. That gives me equilibrium values of 0.026 molar for the butane and 0.064 molar. And again, we could double check to make sure it was back at equilibrium value by taking 0.064 and dividing it by 0.026. That will give me that 2.5 value. And notice that I started at 0.05 and I increased the concentration of my isobutane. It went up to 0.064, which means my equilibrium had to shift left to increase the concentration of my butane. And notice it went from 0.02 to 0.026. Let's look at when there's a change of pressure. If there's an increase in pressure, the equilibrium shifts to the side with fewer moles of gas, reactants, or products. If there's a decrease in pressure, the equilibrium shifts to the side with more moles of gas, reactants, or products. Now, when an equilibrium system involves gases, what happens to the gas concentrations or pressures if the size of the container is changed? The gas concentrations also change if the container volume changes. And if the concentrations change, then depending on the stoichiometry, the equilibrium composition can change. Let's say that I started with a concentration of N2O4 being 0.0280 and NO2 is 0.0128. So if I plug all that in, I get a Kc of 170. But if the volume of the flask holding the gases is suddenly cut in half, the immediate result is that the concentrations of both of the gases will double. The reaction quotient under those circumstances, if the concentrations double, so if I double my numerator 0.028 to 0.056, that's double. And if I double my denominator, 0.0128, I still have to square it. So 0.0256 squared. My Q becomes 85. So Q is now less than K. That's at 170. So to return to the equilibrium, the quantity of the product must increase. Because remember, if Q is less than K, we need to go to the right. So the product must increase at the expense of the reactant. So the new equilibrium composition will have a higher concentration of the N2O4, that's my product, than immediately after that volume change. In returning to the equilibrium, the concentration of NO2 decreases twice as much as the concentration of N2O4 because, look at the stoichiometric ratio. 1 molecule of N2O4 is formed by consuming 2 molecules of NO2. This occurs until the reaction quotient Q is once again equal to K. The net effect of the volume decrease is to decrease the number of molecules in the gas phase. So to sum it up, if I decrease the volume by half, those concentrations will double, which affects the Q. Q then is less than K. And so if I decrease the volume, we need to convert NO2 to N2O4. We need to go to the right. So concentration of N2O4 needs to increase by making my reactants decrease until we reach K. For reactions involving gases, the stress of a volume decrease, when volume decreases, that means the pressure has been increased. It will be counterbalanced by a change in the equilibrium to one having a smaller number of gas molecules. For a volume increase or a pressure decrease, the equilibrium composition will favor the side of the reaction with the larger number of gas molecules. For a reaction where there is no change in the number of gas molecules, then a volume change will have no effect. Let's look at the effects of temperature. What happens when you increase the temperature if we're told we have an endothermic reaction? Or what if we have an exothermic reaction? If we increase the temperature, the equilibrium shifts in the direction that is endothermic. So it uses up some of the added heat energy to counteract temperature increase. If we decrease the temperature, the equilibrium shifts in the direction that is exothermic. So it produces added heat energy to counteract temperature decrease. So in this picture right here, how does the equilibrium of an exothermic reaction shift when the temperature increases? Let's go back to the slide before. If it's an exothermic reaction, temperature increases, so we're looking right here. It's exothermic, it's going to shift favoring absorbing heat. Remember, if we're absorbing heat, it's part of the reactants. If it's releasing heat, that's part of the products. So absorbing heat is going towards the reactants, which is left. If we favored releasing heat, that would be going to the right, to the products. Changing the temperature of a system at equilibrium is different from the other equilibrium disturbances because the value of the equilibrium constant changes with temperature. You can make a qualitative prediction about the effect if you know whether the reaction is exothermic or endothermic. For example, we have an endothermic reaction right here with nitrogen and oxygen giving NO. It tells us that our delta H is a positive value. That means it's endothermic. Endothermic means that heat is a reactant because energy must be provided as heat for the reaction to occur. If the system is at equilibrium and the temperature increases, that means we're increasing the energy added as heat. So the system will adjust to alleviate the stress. The way to counteract that is to use up some of that energy added by consuming more N2 and O2. And if we consume more N2 and O2, that means I'm going to make more products. So we're going to produce more NOs as the system returns to equilibrium. So that raises the value of our numerator because NO is our product. So if I have an increased numerator and therefore a decreased denominator because I'm using these up, so that means the concentration is actually going down, then the value of our K is going to be higher If I have a bigger numerator and a smaller denominator, then the value of my K will increase. Let's look at an example that's exothermic. In this case, this reaction, we have a delta H that's a negative value. So heat is part of my products. By lowering the temperature of the system, some energy is removed as heat. So if we remove energy, that can be counteracted if the reaction produces energy as heat by the combination of NO2 molecules to give more N2O4s. And because I'm going to have more N2O4s, that means my concentration of my numerator is going to increase, and we're using up the NO2, so that concentration will decrease. That's going to give us a larger value of K at those lower temperatures. So in summary, when the temperature of a system at equilibrium increases, the equilibrium will shift in the direction that absorbs energy as heat. So in the endothermic direction, it will shift left. If the temperature decreases, the equilibrium will shift in the direction that releases energy. So in the exothermic direction, which is to the right. Changing the temperature changes the value of K.